Hello everyone. In this presentation, I'll show you my recent work on partially palindromic compositions. Let's begin with definitions. So a composition of n is a sequence of positive integers, alpha 1 through alpha l, whose sum is n. These integers are the parts of this composition. It's well known that the number of compositions of n is 2 to the n minus 1, as they are in bijection with binary strings of length n ending with 1. Now, a composition is called palindromic if the ith part and ith last part are equal for all the i's. The number of such compositions is Pc of n, that equals 2 to the floor of m over 2. Andrews and May in 2021 define a composition to be parity palindromic if the ith part and ith last part have the same parity. Just generalize this to palindromic compositions modulo M by imposing the condition ith part and ith last part are congruent modulo M for all I. And he studied the number Pc and M of such compositions and obtained the generating function for this number. Now, then Andrews and May proved a special formula for PC2n2 and PC2n plus 1, 2. They both equal 2 to the m, 2 times 3 to the n minus 1. And they proved this analytically using generating functions, and just proved this same result using a bijection, and the Vetter used recursion to prove the same formula. And just also showed a formula for PCN3, and that equals 2 to the 2 times n, f n minus 1. Here f sub n is the Fibonacci number. And just gave two proofs, one using generating functions, the other using bijections. And he briefly discussed the case m greater than 3. And shortly after that, Andrews, Just, and May defined a composition to be anti-palindromic if the ith part and ith last part are unequal for all I. And they showed that the number AC of n of such compositions equals Tn plus Tn minus 2, where Tn is a Fibonacci number. So the first three terms are 0, 1, 1. After that, every term is the sum of the previous three terms. And now in our work, we view all the compositions partially palindromic or anti-palindromic, possibly modulo M, and we count them by the extent to which they are palindromic or anti-palindromic. And this is natural to think about, and there's also some motivation from partitions. So a partition of n is just a decreasing sequence of positive integers with the parts adding up to n. And this is similar to a composition, except the parts must be ordered decreasingly. And Euler has a famous result that says the number of partitions of n into distinct parts equals the number of partitions of n into odd parts. And Glacier had a generalization of this result. So the number of partitions of n with no part occurring at least k times equals the number of partitions of n with no parts divisible by k. And if you take k to be 2, you can recover Euler's result. Now there's a further generalization by Franklin that says the number of partitions of n with m distinct parts, each occurring k or more times, equals the number of partitions of n with exactly m distinct parts divisible by k. So taking k to be 0, you can recover Glacier's result. So the way they generalized, Euler's result, is kind of similar as how we want to study partially palindromic compositions. And also there's a parallel story on compositions. You can take the number of compositions of n with odd parts and the number of compositions of n plus 1 with parts greater than 1. They happen to be the same. They're both the Fibonacci number Fn. And this was generalized by Monaghy in 2012 and further by myself in 2020. And that's similar to how Glacier and Franklin generalized Euler's result. Okay, so this provides another motivation for us to study partially palindromic compositions. And let's be precise now. So define uppercase PC super n to be the set of compositions of n that violates the palindromic condition exactly k times. Okay, so And the lowercase pc super k of n is going to be the size of this set. So it's the number of compositions of n that violates the palindromic composition exactly k times. And to study this number, we refine this by taking the compositions that violates the palindromic composition k times with no mid part or an even middle part. And that's counted by pck plus of n. And if a composition violates the palindromic composition k times, the palindromic condition k times, and also has an odd middle part, then we let pck sub minus n count that such kind of composition. And this way we can refine pckm. And for example, PC1 plus of 4 is 2 because there's two compositions, 3, 1, 1, 3, that both violates the palindromic condition once, and they don't have middle part. And there are two compositions of 4, 2, 1, 1, 1, 1, 2. They violate palindromic composition, the palindromic condition once, and they have an odd middle part. So PC1 minus of 4 is 2. And if you add them, you get PC1, 4, that's going to be 4. And we can define ACKN, ACK plus n, ACK minus n in a similar way by requiring the anti-palindromic condition to be violated exactly k times. And we drop the superscript k when k is 0, and that way we can recover the previous results by Andrews, Just, and Sime. And we have a connection between PCK plus and PCK minus, because you can take a composition with an odd middle part and you can subtract 1 from that, you get a composition with an even middle part or no middle part. So PCK plus n is PCK minus n plus 1. So that way PCK plus n is PCK plus n plus PCK plus n minus 1. So we don't have to look at PCK minus of n. And it's the same for ACKN. So let's present our first main results. We have a formula for PCK plus of n, and we also have a formula for ACK plus of n. They're both positive sums of some products that involve binomial coefficients and possibly powers of 2. And we also have two more formulas for ACK plus n. One of them is an alternating sum. And we proved these formulas using generating functions, and we also have combinatorial proof. So that is using bijections for the top two formulas here. PC plus n, so that means when k is 0, we can recover that from our formula for PCK plus n, and it's 2 to the n over 2 when k is even or 0 otherwise. And if you use that, you can recover the formula PC of n equals 2 to the floor of n over 2. And when k is 1, we have another simple formula that's already in OEIS, maybe without this kind of interpretation. So, and the number AC plus n, from our formula, we can get this number by taking k to be 0, and it's a Fibonacci number t prime n plus 1. So the first three terms are 0, 1, and 0. And they still satisfy that Fibonacci recurrence. And AC of n is the sum of t prime n plus 1 t prime of n. So that's slightly different from the formula we saw before for ACN. And we also have another formula for ACKN that specializes to AC of n, and that's tm plus 1 minus tm minus 1. So that's a third formula for AC of n. And next, we want to look at reduced anti-palindromic compositions proposed by Andrews, Just, and Sime by taking the equivalence classes of anti-palindromic compositions under swaps of the ith part and ith last part. And we can define reduced palindromic compositions with k violations, so RPC k of n, or RAC of n. So reduced anti-palindromic compositions with k violations in the same way. And we can also refine them, the plus and minus business in the same way. And for RPC, you just take PC and you divide it by 2 to the k. So that's not so interesting. But for RAC, we have some interesting formula, and that's already in OEIS with a different interpretation in terms of compositions of n minus k with exactly k parts equal to 1. And we can take k to be 0, so we get Fibonacci numbers again. And when k is 1, RAC1 of n actually counts compositions of n minus 2 with at most 1 even part. So that's a different interpretation that possibly, have some connections with our interpretation. And then we can study partially palindromic compositions modulo M. And the definition is very similar to what we had before. Just use a congruence modulo M to define this kind of things. And we have 2 closed formulas, one positive sum, one alternating sum for PCK plus of NM. And when k is 0, the formula becomes relatively easy. And this recovers some known result by just. So when m is 2 or 3, we have nice formulas. And there's also some interesting result when m is even, or when 2n minus 1, so n plus 1 is less than m. Those formulas are studied by just, but we can recover all of them. And also when m is 1, so we can still consider congruence modulo 1. It's kind of trivial, but it's going to give us some interesting result here. And it coincides with the sequencing OEIS that also counts compositions of n with parts greater than 1, each part colored in 2 possible ways. So that naturally raises this question whether there's a bijection between these kind of compositions and the compositions we're studying. And we have another results when m is 1 that, we can take PC plus n1 to get a formula for PC n1. That's just 2 to the n plus minus 1. That's just a number of all compositions of n. Not surprising. But when m is 2, we have another interesting formula that also is already in OEIS. And then we are going to study reduced partially palindromic compositions modulo M. And we get closed formulas that are a little more complicated than before. And we can take k to be 0 to have some simple formulas. And or m is 1. There's some connections with known sequences in OEIS that have some other kind of interpretations. Here we can see, like, for example, compositions of n with increments only appearing at every second position. There's actually a pretty straightforward bijection between these kind of compositions and the ones we use here. And when m is 2, we get Fibonacci numbers again. When m is 4, we can find the resulting OEIS from other perspectives. And so there's more connections we can find to known sequences. And similarly, we can study partially anti-palindromic compositions modulo M. And we get closed formulas that are maybe even more complicated. And we have more formulas for ACK of NM, and we can reduce them to some easier formulas when m is 1 or k is 0 that have connections to various things people studied before, and the various sequences in OEIS. Sometimes we were able to find a bijection, but sometimes is not so clear. And sometimes we even get new sequences in OEIS when k or m are relatively small. And we can study reduced anti-palindromic compositions of modulo M or so. And we have closed formulas. And we have special cases that have connections to many known things. And we also have some questions about connections between those known stuff and our new results. So in summary, we provide a uniform framework for various generalizations of palindromic compositions from previous work of Andrews, Just, and Sime. And we also gives a lot of connections with interesting sequences in OEIS. And we use SAGE to help discover and verify our closed formulas. And we have combinatorial proofs for most of the positive sum formulas. But for alternating sum formulas, we don't have any combinatorial proof yet. Possibly this could be done by inclusion, exclusion, or some other techniques. That's all. Thank you for listening.